Alright, 11.2 Part A. The section is space coordinates and vectors in space. We're going to first do a little lecture on the space coordinates in the first half of the section. Then 11.2b will look at vectors in space. So up to now you've seen how to plot points and look at equations of different curves in 2 dimensions. But here we'll be extending our study to 3 dimensions. So unlike 2 dimensions where you just have the x-axis and the y-axis and 4 quadrants, in the 3-dimensional coordinate system you have the x, the y, and the z-axes, and you notice that it's going to divide the space into 8 octants. So you have planes that are slicing through. So for example, here the xy plane consists of points that have x values, y values, and the z value is 0. Then you have the yz plane where the x value is 0 and y and z are arbitrary anywhere along that side. So they're like walls. The xz plane would have points that have coordinates that'll have an x value, a 0 y value, and a z value. So these points that occur in the 3-dimensional coordinate system have x, y, and z values, and so it's called an ordered triple. So any point is represented as x, y, z, where x is the directed distance from the yz plane to the point P. So this is the yz plane, and the distance from that to to the point P, wherever that is, and so on. So the y is the directed distance from the xz plane to that point. Okay, if the point is somewhere here, let's say z is the distance from the xy plane. It's the height, essentially. So here's some examples from the textbook, some points that are plotted on the x, y, z axes. Notice that to get the 3-dimensional effect, we need to tilt a little bit to see that. Later on in class, I'll be showing you how to use a 3D plotter online that gives us a better 3-dimensional effect. So let's look at this point, 3, 3, negative 2. In order to plot it, the x value is 3, so you start at the origin, go 1, 2, 3 units, and then the y value is positive 3, and that's the positive y-axis, so you go 1, 2, 3 values, 3, and then z is negative 2, so rather than going up, you go down 2 units to reach that point. So you can take a look at how the other points are plotted in a similar manner. In some cases, when we're drawing things by hand, we typically look at it as x, y, and z. Okay, so you have the x-axis, this is the positive x-axis, negative values on the back, the y values, notice the tick marks are slanted, and the z is up here, and in order to give you the 3-dimensional effect, you give it little corners like the wall of a room, okay, the edge of a room. In some cases it is more convenient to have things switched a bit, so you might have, instead of x and y here, you might want to have x here and y here and z here. As long as you label it, you can use either methods, so that gives rise to the orientation, the next topic, and you may see this in physics as well. We have the right-handed system, the first method, which is usually how books represent 3-dimensional system, and then the left-handed system, which is typically used if you have a lot of negative y values, and it's easier to plot it in the front. Alright, moving on. Things you learned in 2 dimensions extended to 3 dimensions, starting with the distance formula. In 2D, the distance formula, and we saw this in class on Monday, it's change in x, x2 minus x1 squared, plus y2 minus y1 squared. And we saw this when we were looking at magnitudes of vectors in 2D. Now in 3 dimensions, it's simply an extra term, where you have for the z2 minus z1 quantity squared, where you have point 1 P with coordinates x1, y1, z1, and a point Q with coordinates x2, y2, z2. And in the textbook, there's a little picture that I've snagged and put in here that shows you how the formula is derived. it's also given to you as a problem set in the book. So looking basically at this cube, a rectangular cuboid, and point P and point Q are labeled like so, finding the distance D. And this part here is a two-dimensional version. You're going from here to here, and then to go from here to there, you basically use the Pythagorean theorem. Something else you learn in 2 dimensions that we extend to 3D. In 2 dimensions, you're looking at the equation of a circle. And you may recall that the equation of a circle was taught to you in this format: x minus h quantity squared plus y minus k quantity squared equals r squared. And in 3 dimensions, you're looking at an extension of that into a sphere. In 2D, the center was hk, and the radius was r, the square root of r squared, which is r. In 3D, the sphere, its equation is in the standard form, in this format, x minus x naught quantity squared, etc., where x naught, y naught, z naught represents the center and r is a radius. In the second half of the section, we'll be seeing more of this. So for now, we'll just look at the standard form. And finally, the midpoint formula. In 2D, the midpoint formula was the average, x1 plus x2 over 2, y1 plus y2 over 2, whereas now you have 3 values. It's an order triple. Basically, you're taking the average and getting the middle point. That's just the midpoint formula. And you'll be needing this to find the center of a sphere. Okay, moving on to some examples that should help you with the homework that I'm going to pass out in class. The first few questions, we're going to look at how to plot the points. So I've got a couple grids here to help us with that. So let's take a look at questions 2 and 4. You'll be doing 1 and 3 at home. So question 2, we're going to plot 3, negative 2, 5. I'm going to call this point A. So 3 is the x value, and x is over here, 1, 2, 3 units. And then y is negative 2, so I need to go to the left 1, 2 units. So it's somewhere in this direction. Okay. And then the z value is 5, so I need to go up 5 units. But 5, 1, 2, 3, 4, 5, you need to draw it parallel to the x-axis to actually get the proper height. So it's there. Okay, so this is the point A. One method to help you with this would be to actually draw a cube. So you start at 3, you go left 2 units, okay, and then you take this cube and raise it up from here 5 units, and that will give you the side and give you the point to plot. Okay, so the second point is 3/2, I believe. I need to check. I didn't copy it so well. It's 3/2, 4, negative 2. So we're going to call this point B. So 3/2 is 1.5, somewhere here. Y is 4, so we go 1, 2, 3, 4 units, which is somewhere here in the 3-dimensional perspective. And the z value is negative 2, so we go down 2 units from there. Okay, and that gives you the point B. Now let's try question 4, where x is 0, y is 4, z is negative 5. So 0 is right here. The y value is 4, 1, 2, 3, 4, and z is negative 5. So that's down in this direction, 1, 2, 3, 4, 5. Okay, so it goes down here. There's your A value, the point A. Point B is 4, 0, 5. Oops. Let's see this better. Point B is 4, 0, 5. So the x value is 4 again. Oh, x is over here. 1, 2, 3, 4. Y is 0, so it stays right there. And then 5 units to the top. 1, 2, 3, 4, 5. So give it that 3D perspective. It's somewhere here. And there's point B. Alright. The next remaining questions that we'll be doing. We'll be doing questions 6 and 8. We'll be doing the odd ones at home, and we'll be doing 24, 28, 34, and 38. Okay, so let's start with 6. It says here, with the description, ooh, what's that? Okay, in the description here, you're told that the point that you need to locate is 7 units in front of the YZ plane, 2 units to the left of the XZ plane, and 1 unit below the XY plane. We need to find the coordinates of the point. So, you saw earlier, I picked a snapshot of the YZ plane. The YZ plane is right here. If you're 3 units behind the YZ plane, as it says in the question, this is the question. So there's actually 7 units in front of the YZ plane. So there's a YZ plane, 7 units in the front, 1, 2, 3, 4, 5, 6, 7. So the X value is 7. And you are 2 units to the left of the XZ plane. So there's the XZ plane. If you're 2 units to the left, so in that direction, Y is negative. And then 1 unit below the XY plane. Here's the XY plane, 1 unit below, which means the Z value is -1. And that's all you have to do after you find that point. And you do the same thing for question 8, where the point we're seeking is located in the YZ plane, 3 units to the right of the XZ plane, and 2 units above the XY plane. So, in the YZ plane, this is the YZ plane. If it's on it, the X value is 0. 3 units to the right of the XZ plane. Here's the XZ plane. 3 units to the right, that's the Y value. And 2 units above XY plane. Here's the XY plane, 2 units above, so it's +2. Alright, I hope that makes sense. The next question is finding the distance between 2 points in space, and we've seen the distance formula for that. If this is x1, y1, z1, this is x2, y2, z2 coordinates, then the distance is the square root of x2 minus x1 squared, so it's 2 minus -2, which is 4 squared, plus change in y, -5 minus 3, which is -8 squared, and then change in z, -2 minus 2, which is -4 squared. And if you calculate that, it's 16 plus 64 plus another 16, which I believe is square root of 96, whoops, which is 4 root 6, I believe. Okay, so I can double check my calculations. Yep, looks good. The next question is also an application of the distance formula. The question says find the lengths of the sides of the triangle with the indicated vertices, so let's call this A, B, and C, and determine whether the triangle is a right triangle, an isosceles triangle, or neither. So we could find the distance AB, distance BC, and distance AC, and see if we get the distances to match up with any of these types of triangles. So distance AB, let's do it real quick. Change in x, 3 minus 0 squared, 3 squared, and then it's 4 minus 6, which is -2 squared, and then 1 minus 2, which is -1 squared. Calculate that, it's 9 plus 4 plus 1, the square root of 14. Distance BC would be 3 minus 0 squared, so it's 3 squared, 5 minus 6, -1 squared, plus 6 minus 2, which is 4 squared. Alright, so that's 9 plus 1 plus 16, which is the square root of 26. And finally, let's figure out distance AC. That will be the square root of 3 minus 3 is 0 squared, 5 minus 4 is 1 squared, 6 minus 1 is 5 squared, so that's the square root of 26. Well, it looks like these two distances are the same, which means it is an isosceles triangle. A couple more questions. Finding the midpoint. Again, to find the midpoint, we just average the x, y, and z values. So let's call M to be the midpoint, add these two, 7 added with negative 5 over 2, 2 added with negative 2 over 2, and 2 added with negative 3 over 2, and that gives us 1, 0, and negative 1/2. Alright, hope that makes sense. It's pretty simple. And finally, finding the equation of a sphere. The standard equation is given by x minus x naught squared plus y minus y naught squared plus z minus z naught squared equals r squared. And in this case, we're given all that, so it's just x minus 4 squared plus y minus negative 1, so it's y plus 1 squared, and plus z minus 1 squared equals 25. And this is the standard form. You don't have to expand this, then it won't be in the standard form. And that's pretty much the end of all the examples. Now be sure to try the worksheet and answer all the questions. I will see you on Monday or Friday.